All right, welcome to our first set of notes for Chapter 15, Acids and Bases. This chapter gets a little bit tricky towards the end, but hopefully if you were in Gen Chem and you recall any of that, the first part of this chapter is really pretty easy. We're going to talk about strong acids and bases first, and so that's where we'll stop for this one, but hopefully this is a lot of review for you is what I'm hoping for. Acids generally are going to have a sour taste. Vinegar, of course, is acetic acid and it just tastes awful. Citrus fruits have citric acid. They'll react with certain metals to produce hydrogen gas, a little zinc strip and hydrochloric acid, and you got bubbles forming. They'll react with carbonates and bicarbonates to produce carbon dioxide gas. And bases taste bitter and they feel slippery. A lot of soaps are made with lye, which is a base. So we're going to work with a Bronsted or Bronsted-Lowry definition for acids and bases. A Bronsted acid is somebody who donates a proton, and a Bronsted base accepts a proton. You'll recall that a proton is pretty much a hydrogen ion. So kind of track the hydrogen, you'll be just fine. And so here we can look at this and say we have NH3 and water. Water becomes OH minus. So to become OH minus, water had to give one hydrogen to NH3 to become OH minus, so water must be the acid and NH3 must be the base. And that's what we would find. So acid and base. Now, because this reaction is reversible, when water gives up its hydrogen, it becomes the conjugate base, meaning it's now able to accept a hydrogen. When NH3 accepts the hydrogen, it goes from a base to a conjugate acid. It's now more able to donate a hydrogen. And so the acid becomes the conjugate base, the base becomes the conjugate acid. Alrighty, so there you go. When it comes to water, water is most stable with H2O, but there is an equilibrium where water will kind of ionize on its own to become hydrogen ions and OH minus ions. So perhaps this backward arrow should be very long and the forward arrow should be very, very short. This is not very energetically favorable, and they don't remain that way for very long. But we call it the auto-ionization of water, which means it's automatic. It does this on its own spontaneously. It just doesn't do it very often. So then that excess hydrogen doesn't just hang around doing nothing. He will bond with the neighboring water and become H3O plus, which we call hydronium, and OH minus will remain as OH minus. And so that's ionization, and here they're just showing you where the hydrogens are going, what it looks like when it's all said and done. And so your net reaction is a water plus a water gives a hydronium and a hydroxide. So here the water, either one would act as an acid and the other as a base. And then this one would become the conjugate base. It's more able to accept protons. Hydronium becomes the conjugate acid. It's more able to donate protons. And so that's how you can kind of look at those. So when water ionizes, we can actually do an equilibrium constant for it. We can say products over reactants, but our reactant is liquid water, which is a solvent. So we really don't need to include him in it. It's really just the hydrogen and the hydroxide. And so we can say, okay, let's call that the Kw instead of Kc. We'll call it Kw, the equilibrium constant for water. And that's hydrogen ion concentration multiplied by hydroxide ion concentration. Now, like I said, it's not a really high concentration. Hydrogen and hydroxide are pretty small, so you're going to find a pretty small number. And we call this the ion product constant. You can just call it Kw if you want. And it's the product of the molar concentrations of H and OH at a particular temperature. No duh, we just finished the equilibrium chapter, so we're not going to worry too much about that. Here's the value for it. 1.0 times 10 to the negative 14. Very, very small number. But that's important. Go ahead and write that in your notes. Hydrogen concentration multiplied by hydroxide concentration equals 1.0 times 10 to the negative 14. That's a constant. That's important to know. It's a very, very useful equation. Alrighty. So the solution is neutral if you have the same amount of hydrogen concentration as you do hydroxide concentration. If you have a lot more hydrogen concentration than you have hydroxide concentration, it's an acid. So think about that. An acid donates protons. So if there's a lot of hydrogens in a solution, then there's been a lot of acid giving up those hydrogens. So it's got to be acidic. If there's much less hydrogen ion concentration than there is hydroxide ion concentration, then it would of course be basic. And so it kind of helps us understand what our solution looks like. So we can use equations like this to solve problems. What's the concentration of OH minus ions in an HCl solution if the hydrogen ion concentration is 1.3 molar? Hydrochloric acid is a pretty strong acid. So saying that we have 1.3 molar HCl is kind of like saying we have 1.3 molar hydrogen ions in solution. And so we know that the hydrogen ions multiplied by the OH ions are 1.0 times 10 to the negative 14. We know that our hydrogen ions from a strong acid is 1.3 molar. You can rearrange this formula to solve for the hydroxide ion concentration. It's 1.0 times 10 to the negative 14 divided by 1.3. Excuse me, you get 7.7 times 10 to the negative 15th molar. That's the OH minus concentration, and that's what the problem asked you for. Later, we'll take that to POH and pH and all sorts of places, but for right now, that's all you need. So pH is a measure of acidity. It means per hydrogen. We use negative log of hydrogen because basically it's easier. Writing down these really small numbers of hydrogen, it's annoying to write 0.00005 or whatever. Whereas to say pH is 3, that's a real easy thing to do. So your formula for pH, go ahead and write this down. Negative log of the hydrogen ions. Could be hydronium, same thing really if it's in water. So if our solution's neutral, then our hydrogen equals our OH minus. And so our hydrogen would be 1 times 10 to the negative 7. That's, half of kW, so that kind of makes sense. And our pH would be 7. If it's acidic, we're going to have more hydrogens, which we've already talked about. Our hydrogen concentration will be greater than 1 times 10 to the negative 7, or half of kW. And our pH will be smaller than 7. If we're basic, we'll flip these. We have more hydroxide. Our hydrogen ion concentration is smaller than half. And so our pH is greater than 7. So as pH goes up, hydrogen concentration goes down. That's an important thing to understand. And so here's kind of a little chart. It takes your pH. They generally say it's 0 to 14. That works well enough. You could start here at acid. Here's bases. So the really acidic stuff, lemon juice, vinegar, orange juice, that kind of stuff. You get to neutral, be about 7. We're talking things like pure water, blood's just a little bit basic. And then we go to household ammonia for cleaning, milk and magnesia as being pretty basic stuff. Here's a pH meter. It's kind of an older one. We can do that with a lot less space nowadays. But we said that the pH was the negative log of hydrogen ions. Well, you can also find something called POH. And POH is the negative log of hydroxide ions. So depending on what the question gives you, you can work with those. Here's a formula you already know. Here's a formula you already know, which is the negative log of the hydrogen ions is pH. The negative log of hydroxide ions is POH. And so pH plus POH has to add to 14. The whole scale runs 14. So if you got a pH of 7, you got a POH of 7. You got a pH of 3, you got a POH of 11. They've always got to add to 14. Oh, you should write this down. That's important. It's very, very helpful. All right, so let's look at a problem here. We take a pH of rainwater. We get 4.82, a little on the acidic side there. What's the hydrogen concentration of the rainwater? And so you can say, okay, if I have pH, I can find hydrogen concentration. Because if pH is the negative log of hydrogen, then hydrogen is 10 raised to the power of negative pH. Go ahead and write that down. It's important. If you're good at math, getting from here to here is very easy. If you're not that great at math, all you need to know is write that down. It's important. So it's real easy. Then we take 10, we raise it to the power of a negative 4.82, and it gives you a hydrogen concentration of about 1.5 times 10 to the negative 5th molar, and that's all the question asks you for. It's a done deal. This one gives us an OH minus concentration in blood, 2.5 times 10 to the negative 7 molar. What's the pH of the blood? So you say, okay, well, I can't go straight to pH, but I know that pH and POH both add to 14, and I know that POH is the negative log of hydroxide ions. So I can go ahead and plug that into my negative log of hydroxide ions and get myself a POH of about 6. Now the problem asks me for pH, so I just take 14 and subtract 6.6 from it. I get about 7.4. For pH of blood, that's exactly where you want to be. Human body is not real tolerant of a wide range of pHs when it comes to blood. 7.4 is a good place. So, a strong electrolyte makes math easy. Strong electrolyte, we assume, breaks 100% of that solid sodium chloride, breaks completely into its ions. There's no solid left. And we like that in the math world. A weak electrolyte is not completely dissociated. Here's your acetic acid example. You get, an acid giving up that hydrogen, but at the same time you get some hydrogen working that back arrow on the equilibrium and going back into this original reactant. These are a little harder to do math with. We can do them. It just makes it a little trickier. So for right now, the book questions you have will work with strong electrolytes, and the world will be a simple place, and we like that. Strong acids are strong electrolytes. For right now, you can assume we're working with strong acids. Hydrochloric acid is going to split. Every little compound is going to split into just hydrogen and just chlorine. So we can assume only a forward reaction to hydronium and chlorine, and that makes that real easy. Here's nitric acid, same thing. Probably perchloric acid, I could be wrong there, gives you the same thing, and sulfuric acid gives you the same thing. So we're going to assume everything we're working with is strong acids for right now for your first section of book problems. That's all you need. And if you know that pH is negative log of hydrogen, and pH plus POH is 14, and that KW is 1 times 10 to the negative 14, you'll probably be pretty well off for this first set of questions. So that's really all you're going to need for the first part. We will save weak acids for our next section. Things will get a little trickier, but for right now, that's where we'll stop. So thank you.